All right, I hope everyone had a good weekend. Let's see where we're at here. So we have, our next test is October 17th. It's Wednesday, so we've got a couple of weeks here. Today we're going to start the last section on techniques of integration. So this will be, we're coming to the end of, how do we find antiderivatives? And then we're going to talk a little bit more about exactly where the antiderivative comes from in terms of, I told you early in the semester we'll talk about where this symbol comes from. And then we'll start putting those numbers on the ends of this and trying to figure out what that means. And then we're going to do, I guess we'll finish up with 6.6 improper integrals, and that's what the second exam will cover. So, all right, that's where we're headed. Now, I'm sure you had fun with 6.2 homework. Yeah, that was a lot.
61 so.
Yeah, there's a lot of problems, right? So, if you remember 6.2, it was like two different ideas, right? We had trig integrals, like cosine, sine, and then tangent and secant. And it took us 2 days to get through it, right? With partial fractions, we have the same sort of thing. We have, it's not two ideas, but it's going to take us 2 days to get through it. Today, all we're going to do is just prepare ourselves for partial fractions. And that doesn't mean I'm going to go review partial fractions. What we're going to do is look at the types of integrals that we should be able to do at this point. All right, and you may be saying to yourself, well, if we already know how to do them, why are we going to do them again? Like, why go through it again? It's because most of these don't look exactly like something we've seen, or we're going to extend the ideas that we have already and kind of generalize things. So, all right, I'll shut up. Let's just get going here. All right, so first thing I want to point out is that we had a formula that I asked you to remember, and it was this one right here. I said this comes up a lot, and I told you that the antiderivative of that would be arctangent of x plus c, right? Okay, so we have a more general formula. It's formula 17. It's on your formula sheets. And this formula has a slight little tweak to this formula, and that's, this formula is good if that's 1, right? But in general, if we have some a squared there, so in this case, this would be 1 squared. Now, u here is like x, all right? We're treating u like the variable x because integrating with respect to u. So if that's any number squared, then here's the more general formula for it, all right? And you can see here that this would actually work. This formula works with this because a is 1 here, right? So if I put like 1 over 1, right? 1 over a, and then tangent x over 1, then it's the same thing, right? So
A was x in this.
No. The x is the u. Because remember, it's dx, du.
Okay.
So u is the variable here. A is the constant. Oh. Way to go, man. No, I don't think you moved it. You're good. I've had that happen before where I had an entire lecture, the camera's like over here. And someone hit it and didn't say anything about it. So I was, and then other students were like, hey, your camera was messed up. I was like, all right, what can I say? All right, so let's see if we can just use an example real quick to make sure we understand this. What if we have arctangent? Gosh, man, I need to wake up. Okay, that's dead. How about this? Let me just take a big shot of this right here. So what would this be? So what's A? That's got to be A squared, right? So A is the square root of that. So A is root 2. Okay? Understand? So this is going to be 1 over root 2. arctangent of, in this case, x, right, for us? X over root 2 plus c. So that's how that formula works. So anytime we see our variable squared in the denominator plus some constant, then we can go right to this, can't we? There will be no real technique, so to speak. All right? Now, let's talk about some integrals that we should be able to handle at this point. And there's going to be 8 of these that we're going to do right now. It's going to take us most of the class. So here are some integrals we should be able to handle at this point, and we're going to confirm that we can do that. So how about this one? And what I want you to pay attention to here is the format of the integral. We have a constant, right, 2, over a linear expression in x. Anytime we see a constant divided by a linear expression in x, we can always make a basic U substitution. And that U substitution will be the linear expression. And the reason is because if I look at this linear expression, if I take its derivative, right, if I let this be u, the derivative of that will be a constant, won't it? And I have a constant up top. I might be off by a constant, but I'm going to be within, I guess, a margin of error of a constant, so I know it'll always work, right? Does that make sense? So I let u be x minus 4, then in this case du is what? Just dx, and well, I have 2 dx, don't I? Well, now I could pull the 2 out, couldn't I? If I pulled the 2 out, then I would have a 1 dx and it would match perfectly. So I have 2 options here. I can either pull the 2 out, or I can just multiply both sides of this by 2. Either way, right? And it would match. I'm just going to choose to pull the 2 out. So this is 2 integral, and then what does this turn into? 1 over u. And then du is dx, so du. And then what's the antiderivative of 1 over u? ln absolute value of u, right, plus c. And then what is u? X minus 4. Okay? So that would be the procedure that we would go through for this, right? So anytime we see a constant over a linear expression, we would have this, right? We would have a natural log. Now let's look at number 2. Because number 2 is just a slight tweak of this. If we have a constant over a linear expression. Now I don't want to write things down. I don't want to actually put down what u is. I want us to think through it, okay? Because really, the things we're looking at here, what we're going to be doing later, I should probably show you, just to give you a glimpse as to the problems we're going to be doing later. We're going to be taking each one of these and integrating them, okay? So what we need to do first is we're going to have to do partial fraction decomposition. And if you remember that from college algebra or pre-cal, right? Pre-cal is where we do it here. What we do is we take this and we break it up into a bunch of little pieces. And each of those pieces is going to look like one of these 8 that we're practicing right now. And so we don't want this to take us, 5 minutes to go through a U substitution here. We want to be able to almost think through the answer. So that's what I want you to do right now, is just think through this. Here, constant over linear, I can let u be the denominator, right? If u is the denominator, then the derivative of that is going to be what here? Negative 5, right? dx. And I don't have a negative 5, right? So I would have to divide both sides by negative 5, right? Another way to look at this is, do you remember when we were doing things like this? Cosine of ax plus b. Do you remember that, dx? Do you remember that the antiderivative of this is going to be sine ax plus b? But what do we have to do out front? 1 over a. And didn't that 1 over a that was there to compensate for the fact that when we take derivative of this linear expression, the a is going to pop out and we want to kill it off? Yeah. Same exact thing here. This looks like 1 over u, right? But we're going to have to scale it, in this case, by 1 over a, which would be 1 over negative 5, because we've got a negative 5 in front of the x. So without doing any work, I'm going to do this. I'm going to scale by 1 over a, and then I know it's going to be natural log of u, which in this case is negative 4 minus 5x plus c, like that.
You can just do that every time.
Yeah, we want to get to a point where we're not writing anything down but this.
So you
Okay.
just do the u sub of the bottom of your head. Okay, that's the constants coming out.
Yep. You just need to think to yourself, this is 1 over u, right?
Yeah.
The antiderivative is natural log of u. However, because it's a negative 5, I need to scale by 1 over negative 5.
Yeah.
Yep, that's it. Okay? Let's just do another one real quick to see if you're getting this. What if we have 3 over, let's do, I don't know, 7x minus 1 dx?
1/7.
So we know we have to scale by 1/7, right?
Yeah.
But we also have a 3 up here. That 3 would have come out, right? And then 3/7. I'm going to do it that way. 3 over 7, because that's 3 that came out times the 1/7. And then what? Natural log of 7x. Yeah, absolute value. That's it, right? Okay, so we want this to just be like really quick. Understand? I mean, if you really had to at this point, you could do u substitutions and get it, but it's just going to take you longer. And as you know on a test, you want to be able to finish, right? So you don't want to be taking up time doing this. Okay, so far so good? That's how you handle a constant over a linear expression in x. What if we have a constant over a repeated linear factor? So notice we have a linear factor, right? A linear expression, but it's being squared. Yeah? Well, could we make the same substitution? U is 2x plus 1. Yes? Okay. And then it would look like this. It would be 1 over u squared instead of now, not exactly, because we would have a 2 here, wouldn't we? So we'd have to scale it by 1/2. But this antiderivative is not natural log. That's a little bit different, right? This is u to the negative 2 du, right? So what's the antiderivative of that?
Negative 1/3 u to the negative 3.
Close. Negative's right.
Oh, wait, u.
U to the minus 1. That's all it is, plus c. So we're adding 1 to this, right? That gives us negative 1. Then we have to scale by 1 over negative 1, which is still negative 1. This is just power rule to here, all right? So do you see that we're going to have pretty much the same thing we had a second ago? We still have to scale by 1 over a, but our antiderivative is not natural log. It's this. Does that make sense? Okay, so let's try and do this without doing any writing down of substitutions. We know automatically this is going to be 1/2, right? Then times, now we're thinking to ourselves, we've taken care of the 2. Now this is 1 over u squared. The antiderivative of that is negative u to the negative 1. So I'm going to write this down. How do I want to write this? Negative u, what's u? 2x plus 1 to the negative 1 plus c. Yeah, I can move it to the denominator. And I don't like this notation, this 1/2 times negative. Someone might think that's subtraction. The dot is absolutely essential here. That implies that this is not subtraction. But just to clear up all doubt, let me do it this way. Negative 1 over 2 and then 2x plus 1 to the first power on the bottom. So that's the same expression, right? That 2. This drop down. Now you could also pass that 2 through if you wanted to. You could do that, but I'm just going to leave it. All right? So there's your antiderivative. Let's do another one of these. What if we had 4 over 5 minus 3x to the 4th power dx? So you look at that, you realize you have a constant, right? Over a repeated linear factor. Linear factor repeated. So this looks a lot like 1 over u to the 4th, right? 1 over u to the 4th. Yeah, so, and we're also going to have to compensate for this right here. And the 4, we're going to have to take into account that. And maybe it might be worth it real quick on the side just to think about what would what would the antiderivative of 1 over u to the 4th be? So this is u to the negative 4 du, right? So this would be negative 1/3 u to the negative 3. That's what the antiderivative of this would be, right? So maybe you need to jot that down. That's fine if you do. We're trying to avoid going through the entire u substitution. Okay, so now let's try and get this. All right, so the 4 I need to take account of, 4. I have the 3 here, so negative 1/3. And then I have another, because of the actual integration, I have a negative 1/3 again. And then it'll be u, which is 5 minus 3x to what power? Negative 3 plus c. Does it seem like I'm trying to get you to do too much at one time? Okay, what is this, 4/9? Yeah, you know what? Let's drop that down. 5 minus 3x to the 3rd plus c. That looks terrible. Let me move that 4 into the middle here. There we go. Feel better about that. Any questions? Sure? Again, this is not anything really new that I'm doing. It's just that we're trying to do it a little faster and a little more efficient, right? That's the only thing. Okay. Moving along. Well, that's the same thing, right? See if you can get that one. See how long it takes you to get that one. This one's pretty straightforward because a is 1 in this one, right? So you don't really have to scale out by much. Raise your hand when you have it. I want to just see how long it's taken people. Okay, good, okay, good. You can put them down. Just trying to get a feel for when we're about 80% there. Take its derivative, right? You can check it. Okay. Let me see here. I'm just going to pick somebody randomly. Let's see what happens. All right? Someone tell me when to stop. Jonathan Garcia. Where's Jonathan? No? Lucky. Okay, tell me when. Amir? Perez?
Not here.
Joseph Martinez. That's all right. Good, Joseph. Good.
So I got negative 1 over 2 times x.
Negative 1 over 2 times x minus 5
Squared.
plus.
Plus 3.
What is he? Yes, he's all right? Yep, good. Yep.
Don't you have to double the negative 1/2 since you're compensating? Or
Well, there was nothing to compensate for because the number in front of x was 1, right? So our 1 over a was 1 over 1. Yes? You see it? So we all agree? Anybody have any questions? Do I need to go through it? We're all good? Okay. Good job. See, why were you upset? Okay. So far, I don't think there's anything really new, right? I mean, all right, so what about this? We have a constant over a quadratic, right? This is a quadratic expression down here, right? Constant over quadratic. We can handle constant over linear. Would you agree? It looks like we can handle that. Constant over quadratic. However, our quadratic does not have an x term. It has an x squared term, and it has a constant, but there's a missing x term. Agreed? So how do we handle that?
Isn't that the same thing we did with inverse tangent?
Yeah, that's arctan, right? That's formula number 17. So there should be no work here. We should go straight to formula 17. What's a? Because in the formula I started class with, we have an a to think about now. A is 3 here. So it's just going to be 1 over 3 arctangent of x over 3 plus c. And we're done. Right? Okay. Now what about something like this? Well, you know what? What if that was a minus 9? Would the formula work? It wouldn't work because that formula says it has to be a plus. If it was x squared minus 9, couldn't we factor the denominator? Because then it would be a difference of squares, right? And if we can factor the denominator, then we will have a way of doing it, and that will be next class, okay? So for right now, we can handle a quadratic missing an x term so long as there's a plus between them, right? Okay. Let's try and tweak this one just a little bit. How about that? Yeah, so we have an issue here because in the formula that we have for number 17, it was u squared plus a squared, right? U squared. And u is going to be our variable squared. It does not have, we're assuming in that formula that the coefficient on that is 1, right? And here, the coefficient on the square term is 4. Well, there's an easy way to take care of that, and that's just factor a 4 out of the bottom. So let's just pull a 4 out. So if I pull a 4 out of the bottom, it'll come out as a 1/4, right? And then if I pull a 4 out of this, I have x squared. And if I pull a 4 out of 1, that has turned into 1/4. So if that 4 goes back through here and here, then we get back this. And now, what's a? 1/2, right? So this is your u squared plus a squared. The square root of 1/4 is 1/2. So this will be 1/4. That's this 1/4, right? And then the formula, which is 1 over a, what's a? 1/2. That's going to flip and become a 2. Okay, arctangent of x over 1/2 again plus c, and I can flip that half up and make that 2x. So at the end of all this, this 1 over 1/2 becomes a 2. 2 times a 4th is a 1/2. Arctangent of 2x plus c. It'll work. If you take derivative of that, you will get this. Question, yes?
So when using the formula, I know we take the square root of u or a.
Of u or a?
Or both u and a, sorry. Like, square root of u, sorry. Like, to get u by itself, we square root the u squared. Right?
Okay, yes, all right.
So, like, I'm going to use the first answer for example.
Okay.
Like, I know that the square root of 9 is positive 3 or negative 3. If we get positive, it turns out positive, like our answer is. If we get negative, it's double net. Both, there's 2 negatives, and it'll turn the answer positive.
Like
if we get 2 negative 3s in there, they're going to cancel each other out, would they?
No. I see what you're saying. You're saying when we are looking at a squared as being 9, we are always going to take the principal root. The principal root is the positive root. Okay? So a will never be negative in these formulas. It's always going to be the positive answer.
Okay, that's just general.
That's just general, yes. It actually comes from the fact that to actually do this problem, like I should say to come up with the formula. If you wanted to actually come up with the formula, 1 over a arctangent of x over a plus c, then what you would do is you would rewrite this integral like this. Square root of x squared plus 9 squared. So isn't that x squared plus 9, isn't that the square root of x plus 9 squared? That's just me just being clever. Now I would use trig substitution. And remember in trig substitution, what we would do is we would notice we have something squared plus something squared under a root, right? So we would make a trig substitution, x is equal to, in this case, because they're added, it's x squared plus 9, it would be a tan theta. Okay? Tan? Yeah, because tan squared plus, yeah. So the a is positive. Now, why is it positive and not negative? Let me show you. Because on our reference triangle, right? When we did a reference triangle off of this, we're talking about sides of a triangle, and we wouldn't want to have a negative side, right? We measure the lengths as positive numbers. So that's kind of where it's coming from. Does that help? Okay. So when you're doing when you're looking at the formula and you're trying to figure out what a is, always take what we call the principal root, which is the positive square root, right? I still don't think we've run into anything too messy here. We might finish up early, huh?
Oh.
No.
Oh,
Yes.
sorry, in that last problem?
Yeah.
You know how it was like, you kind of sucked the 4 out?
Yeah, yeah.
And then you got 1 over 4,
Mm-hmm.
and then you divide by 4 to get rid of it. Well, if you say you take the principal root,
Mm-hmm.
you can just take the square root of 1/4, and then you know it's 1/2, because it ended up being 1/2 anyways.
I'm not sure what you're asking me. Okay.
Last one you showed me.
4x squared plus 1, the original problem. Can't I just do what?
So you divided by 4, like you took a 1/4 out,
Yes, I did.
right? So then you got plus 1/4. That would
Right
be
here.
a. You take
That's
the
a squared.
A squared, yeah. So you take the square root of that.
Yes.
So it's just 1/2.
Yes.
So couldn't you just do that first?
Do what first?
You said you take, you called it the principal square root, so the positive square root of that,
Mm-hmm.
because that's a squared.
That's
couldn't
a
just
squared.
do that first.
I'm not sure what you mean by do that
Take
first.
the square root of that first.
I thought that's what we did, though.
Yeah.
That's what we did. We pulled the 4 out.
Yeah.
We got this, and then we said, what's the square root of this? And we said 1/2. I didn't say principal root. I just said square root.
Yeah.
And we got 1/2. And we
Okay,
said,
never mind. That's
yeah.
okay.
I think that's what we did. That's why I'm confused with the question.
No, never mind.
Okay. All right, let's look at the next one. All right, so now how do we deal with a constant over an irreducible quadratic? Now, what does irreducible mean? Can't factor it, okay? Cannot factor this denominator. You go ahead and try it yourself if you want. You can't do it, all right? You can't factor it over any nice numbers. Yes? Well, yes, we will complete the square, but if it did factor, we are going to have a different way of doing this. That'll come next class, all right? Remember in the previous problem I said if that was a minus, we could factor and we would do something? Okay? We will deal with that later. This one, if we could factor, we will do something. But if it doesn't factor, how do we go about doing it? And so what we'll do, and this will be the standard technique for this, a constant over irreducible quadratic. And let's not lose sight of the fact that this is constant, because we're about to have something else up here. So constant over an irreducible quadratic, we will complete the square. All right? Complete the square of the quadratic. So going back, we did this, right? Last class, or one of the previous classes, we had to do some completing of the square? Yes?
Yeah.
Okay, so we're all professional completers of squares now. So we just take half of this, right? Which is 1? and then square it, which is still 1, and then we add and subtract it. So this is where we had that 2x, we had that hidden 0. Let's see if any of these markers work. Not bad. So we're going to add and subtract 1. That's our hidden 0, and then we have still plus 17. And now, the first 3 terms always factor to be a perfect square trinomial. So it's x plus 1 squared. And then the last thing I have here is plus 16. Okay? All right, so now I rewrite the problem. This is integral 1 over 1 plus x squared plus 16 dx. Now I'd like for you to just squint your eyes when you look at this. Come on, squint. I only see one person squint, 2 people now. Doesn't this look a lot like 1 over u squared plus a squared? Doesn't it? 1 over u squared plus a squared? Except the u that we have is not just x, right? It's x plus 1. So if I did just a real quick little basic substitution, u is x plus 1, then it would look like 1 over u squared plus a squared, yes? We would also have to worry about possibly the derivative of this throwing a constant out that we would have to compensate for. In this case, the constant it throws out is a 1, so it doesn't matter. So can we go straight to the answer then? Do we have a formula for 1 over u squared plus a squared? It's arctangent 1, right? So I hope you're okay with the idea that because this is a 1, I don't have to scale by anything. And then I just have, what's the formula? 1 over a, right? A in this case is the principal root of 16. 1/4 arctangent. Now this is where things are going to be a little bit different. It's not x over 4, it's what? It's x plus 1 over 4. Because x plus 1 was the u, right? You see how if this had been like, let's just say this had been 3x plus 1, then we would have had to have a 1/3 out here.
That's
Question?
what I was gonna
I
ask.
thought I saw a hand. Yes.
If you take it out.
Yeah. If there was a 3 in here, if after completing the square that happened, well, it actually won't ever happen because this won't ever have a number. Because remember, our first step is to make sure that this is a 1. So if there was a number, you would actually have it outside the integral already. So you won't ever deal with that. But you know, you never know. Someone could just throw an integral at you like this. Just here it is, and they just put a 5x plus 1 squared here, and so you need a 1/5 out there.
Which would make that 1/20th.
That's right. Mm-hmm. Is that okay? Just complete the square. Ah, this one's different. Irreducible quadratic on the bottom, and not a constant on top. What's on top? A linear expression. Okay. So let me start this with this. I've seen this done different ways. It's taught different ways, all right? It really just depends on your professor's preference. I like to show this problem in like how to handle this in a somewhat unorthodox way, but I think it's very valuable in terms of some of the cool stuff we can do in math. It kind of shows you like a different way of thinking about things. Whereas I could show you something that's more like systematic, but I don't think it's as constructive like long term for you, okay? So here's the way I want you to think about this. If you have a quadratic in the denominator, right? And you take its derivative, like so let's say we did a u substitution right now, and u was the denominator. Then the derivative of that quadratic should be linear, shouldn't it? Because when you take derivatives, the powers on everything go down. So if you start quadratic, take its derivative, it'll be linear. So wouldn't it be awesome if we let this be u, and we took its derivative, and the derivative was exactly that expression? It's not, but wouldn't that be nice? Do y'all agree with me? Okay, so let me just kind of write out what I'm thinking. Like, it would be nice if I could let u be 4x squared minus 4x plus 3, and then the derivative of that, 8x minus 4, that's the derivative, right? Wouldn't it be nice, you know, if this right here matched and it was x plus 1? Wouldn't it be really cool if that was x plus 1? Because then we'd be done, wouldn't we? It would just be like 1 over u du. So my question is, can we turn this into x plus 1? And I want you to be very careful here, because you have to, whatever you do has to be algebraically correct. Can we turn that into x plus 1? Or x minus 1, sorry, x minus 1. Can we turn that into x minus 1?
No.
We can't. We could pull a 4 out, right? And then divide the 4 out. Let me see what would happen. If I divided 4 out, I divide 4, I'd get 2x minus 1, wouldn't I? And that's not quite x minus 1. If I try and divide this 2, like divide 2 here, that'll turn into a 1/2, won't it? And that won't match. So there, it doesn't look like I can do anything here that's going to make this turn into x minus 1, right? But wouldn't it be nice if it was 8x minus 4 up there? It would be nice. So I'm going to make it, okay? I'm going to make that 8x minus 4, okay? Here I go. So this is my goal. I want the numerator to become 8x minus 4. All right, so the first thing I'm going to do is this. And I want you to tell me if this causes you some problems. Like if this bothers your logic. Because I just want to see what your reaction is to this. Okay, what do you think about that step? Am I allowed to do that?
Yes.
Can I just multiply the integral by 8 just out of nowhere? Only if I put a 1/8 outside. Now, does that seem to be more logical?
Yeah.
Because really what I did is I put an 8 over 8 out here, didn't I?
Yeah.
And then I passed an 8 through
Yeah, you can
the top, and I kept the 1/8 out here. So all I'm doing is just rewriting it. It's the same expression, yeah? Just kind of being clever. Now I'm shooting for 8x minus 4. So the first thing I did was I created the 8x, right? Now I need minus 4. So what I'm going to do next is kind of use that hidden 0 idea. And I understand that I could rewrite this as minus 4, okay? But sometimes this is a fraction and you can't do this. So what I'm going to do instead is I'm going to say I'm trying to get a minus 4, right? So I'm going to put it there. I'm going to go minus 4 plus 4. Okay? And then I still had what up there? Minus 8, right? I can't get rid of that. That's still there. And then over 4x squared minus 4x plus 3 dx. Y'all with me? Okay, now this is 1/8 integral 8x minus 4 over 4x squared minus 4x plus 3 dx. So I haven't quite pulled it off, have I? I mean, I've somewhat pulled it off. I put these two together right here, and then these two I combined, right, like this. Like, if that minus 4 wasn't there, I'd be there, right? I'd be there, yeah? So watch what I'm going to do. I'm just going to split this into 2 separate integrals now, all right? So what would happen if I split this into 2 different integrals? I would have 1/8 integral, and my first integral is 8x minus 4, right? Over the denominator, 4x squared minus 4x plus 3 dx. And I know this integral is going to be nice, right? I designed it that way. Now, the other integral is going to have what in it? I have a minus 4 on top, and I have a 1/8 out on the front, right? So when I pop that negative 4 outside, it'll become negative 1/2. Agreed? And then integral of what? 1 over 4x squared minus 4x plus 3 dx. Now this one right here, I can handle, again, because I made it so I could handle it, right? Now what about this one? What do we have now? A constant over an irreducible quadratic. Complete the square. Okay? So what I started with was linear over irreducible quadratic. Unfortunately, the derivative of the bottom was not the top. I was hoping for that. So I made that happen. But the consequence of that is that it left me with a constant over my irreducible quadratic, but I'm okay with that because I know how to handle that. Does that make sense? So I'm ready to keep going here. All right, let's go. Let's do this one right here. This one we should be able to do without doing any work. We know that this is u, right? We know the top is du. So this is just 1 over u du. So natural log of u, yes? But then we have the 1/8 out front. Do I have to compensate for the 4 or anything, or? No, because the derivative is exactly the top. I mean, it's so we already have that taken care of. So, but we still have the 1/8, and then it's natural log of 4x squared minus 4x plus 3. Okay, and then minus 1/2 this integral. And I'm going to come back to this. I'm actually going to go complete the square over here real quick. So, like I said, I like this method because it requires that you do something kind of outside the box a little bit. You're trying to like achieve a goal, so you make something work a certain way for yourself. You know what I'm saying? You're just using arithmetic. That's it. If you do this, you'll always wind up with a constant over your irreducible quadratic out here. That'll always happen. All right? You'll have the piece that works, and then you'll have the piece that you can just use completing the square on. Yes?
Is that kind of like when we do integration by parts, it kind of like takes off the power and it keeps taking off the power and power?
Yeah.
Something like that?
It's the fact that if I could have started the problem. Look, I could have started the problem with this over the denominator, whatever, right? And then minus another integral 1 over the denominator. Couldn't I have done that, like split it right here?
Yeah.
And then this would have been here, right? Like that's basically what this is out here. Now I have the negative 1/2, but I could have started the problem here. Now for this one, you could still do the same idea. You could do like 8 here, 1/8 here, right? And then you could do, oh, well, I need a minus 4 plus 4, right?
Would have been the same thing.
And then you would have said this and then split it into 2, right? And then you would have had the 4 over this. Every single time, this right here, because of this hidden 0, this is always going to be a number, right? And that's going to be over your quadratic. So you're always going to get constant over quadratic every time. Because the linear part you're taking, you're kind of grabbing that and using it. That make sense? Okay. But I don't recommend you do it that way because you actually have to then combine 2 integrals together at the end. It's better to just do it all at one time. Okay, let's complete the square. 4x squared minus 4x plus 3. So how do we complete the square on that? First step. Pull the 4 out, right? 4 comes out. And that's going to wind up coming out of my integral, okay? But I'm just going to work on it over here. X squared minus x plus 3/4. That's what I get when I pull a 4 out of everything. The number in front of x is negative 1. Take half of that. Negative 1/2. Square it. 4th. So I'm going to have a hidden 0 here. 1/4 minus a 4th, right? And plus 3/4. What do those first 3 terms factor to be here? So here's 4. Should be x what? X minus a 1/2. And then plus this together, right? Which is just 1/2. That's 2/4. So that's what that denominator is, right? Okay, so let's do this. This is, can I squeeze that 1/4 in here? That's why you write in pencil, right? Because now I've decided I'm going to take that 4 here, which is on the bottom, and pop it out here as a 1/4. And that leaves me with my x minus a 1/2 squared plus a 1/2 dx. And what does this look a lot like? Arctan, right? This is 1 over u squared plus a squared. U is this little linear expression. I have a 1 in front of the x, so I don't have to worry about it, like compensating for that. So this is minus 1/8. Now be careful here, times. What is a here?
1 over square root 2.
1 over root 2, right? 1 over root 2. The square root of that principal root is 1 over root 2. Just take the root of the top and bottom. So I have out here 1 over root 2, arctangent of x minus a half, that's our u, and then over 1 over root 2. I mean, you could like do 1 over this, flip it, right? And this would be like root 2 over 8. This 1 over root 2, that, I have to sneeze. You could distribute a root 2 through here, right? Okay, let me write it. Your next line, you could. I'm happy. If you wrote that on a test, I'd be happy, okay? Because, especially I'd be happy because it's easy for me to grade that. Like I can easily see what A is here, right? You haven't messed anything up yet, you know? The arithmetic hasn't been messed up yet, right? Arctangent of, so I would bring the root 2 up and it would just be like root 2x minus root 2 over 2 plus c, something like that. Understand what I did there?
Question for the answer. We have to put a plus c after the 1/8 ln.
We do not have to put a plus c here because we were still working with an integral, which was going to spit a plus c out at the end. So I was just about to say, your final answer is this, right? And then with that attached to the end of it, right? It's this minus this right here, plus c.
That just looks weird. Root 2x.
Mm-hmm. We're not used to seeing irrational numbers in front of our constants. Let's do a little side thing while I'm thinking about this. We're going to have time here. I know some of y'all have had me before, so I may have talked about this before, but I apologize ahead of time. Some of you all have been taught to never leave radicals in the denominator, right? Like that's like a big no-no. Some instructors are very particular about this. And so when I was a student, I didn't quite understand what it was that made it so important for me to have to not do that, right? Like why get so upset about me leaving that there? So what would, for those of you who've been told you can't do this, what are you told you're supposed to do at this point? Multiply by a 1, and that 1 needs to be root 2 over root 2 here. We call this rationalizing the denominator. Okay, so if we do this, it becomes root 2 over, and this becomes 2, right? So we have this, and now let's put that up against the original expression like that. And I'd like for us to discuss this. If you get on your calculator and you type this in, you're going to get a number, right? Do you want to do it? Go ahead. Root 2 over 2. What do you get? 0.707, right? Something like that? Blah, blah, blah. There's more decimals. Okay, so what about 1 over root 2? You better get the same thing, right? Now, we should get this. We should get the same thing because all we did was multiplied it by 1, right? So why? Why have you been told, almost to the point of it almost being told this is wrong, right? When it's numerically the same answer. Did I tell you all this?
Yeah.
I did, right? Okay.
So you're saying
Yeah.
it doesn't matter which one we have?
They're the same answer.
So it doesn't matter which one we
Well, does it matter?
have? I don't know, I'm asking
Were
you, what's your preference?
Well, I want you to think about, why have you been told that, were you ever told not to leave this?
Yeah, they just said it looks ugly.
It looked ugly, okay. Do you buy that though? I mean, if it's the same answer, see, I'm saying from my point of view as a student, I didn't understand why this was wrong and I had to do this.
Aesthetics.
Aesthetics? Is it aesthetics? Because if it's aesthetics, I don't like that. You know, like, it's correct, right? So as a student, I looked more into this, and there actually turns out to be a historical explanation to it. It's been taught to the point that they will tell you, this is wrong, you must do this, right? But the reason why is because they were told they must do that, and the person who taught them was told they must do that, without actually really thinking about what's going on here. So here,
guy started the chain a long time ago.
well, it was a lot of people that didn't. So let's think about it. Before computers, before calculators, all right? Let's say that somebody came across this in a math problem, which I think it's reasonable to think that you might have to calculate 1 over root 2. So before calculators and computers, people had to have things memorized. So like root 2 was just one of those numbers you needed to know what it was, approximately the decimals. It's like 1.41 something. So you would have to have that like stored, okay, in your brain. Pi, you had to have that memorized, 3.1415, whatever, you know? And there used to be like contests, you know, like who knew pi out the furthest. There's still people that do that, but not as much because of computers. In fact, there's a faculty member here who's in his 60s that actually at one point in time knew pi out 120 decimal places. And when on his 60th birthday, did I tell you all this story?
Yeah.
I told you that story too. On his 60th birthday, he had a birthday cake made for him that was really long, and it had a bunch of wax candles, and it was pi out 60 digits for his 60th birthday. And he did the whole thing. He turned around, didn't look at the cake, and did 60 digits out. So like even 65 years old, this man could remember pi 60 digits. That's what you had to do back then. You had to just have these memorized, okay? All right, got that? Okay, now, you're one of these people without a calculator, and you've got to compute 1 divided by root 2. Let's try and do this, okay? So we have to do it by hand. We don't have a calculator. So we put 1 in the division box, right? And then we put root 2 out here, which we'd have to have memorized. So that's about 1.414. So well, let's just go with that. All right? So how do I do that division? Well, first thing I do is I say, does 1.414 go into 1? I say no, so I bring a decimal up, right? Then I start thinking, does 1.414 go into 10? Yes? How many times? I don't know. Maybe about 6 times. That's kind of tough, right? Do y'all understand that's kind of tough? Okay, that's weird to do that, right? I mean, it's going to be messy. Now, instead of doing it this way, let's do it this way because it's the same answer, right? So now when I do the division box, what goes in the division box? The root 2, which is 1.414, right? What's on the outside? 2. Now, does 2 go into 1? No. Bring your decimal up. Does 2 go into 14? 7 times. Bring down this. Then you just do arithmetic. It's a lot easier to put an integer into a decimal than it is to put a decimal into an integer. Does that make sense? That's why. That's why you want to rationalize your denominators, because arithmetically, by hand, it's easier to do. This is obsolete. Do you understand that? This is an obsolete thing. Yes?
So we were doing it for, I guess, the easiness of the older generation to compile it and solve it?
I think what happened is, this happens a lot in math. Things are taught, okay? This happens especially in grade school, middle school. You have people who are teaching things, and they're teaching it the way they're taught. And this is, unfortunately, in the United States especially, a lot of people who teach elementary, middle school are, yes, they can do math. I'm not trying to like talk bad, but like I was talking to someone in the class about this. They might know the quadratic formula, but they don't know how to derive it themselves. You know what I'm saying? Like if someone ever came to them and said, hey, where does a quadratic formula come from? They'd be like, I don't know. You know, so like the level of understanding is very shallow. And so I think that's what happened throughout history is this was absolutely a necessary thing if you wanted to do arithmetic. And so they were told, look, every time you see this, you have to turn it into this, have to. And then that just kind of snowballed into, it's a rule, you know? And no one's ever really questioned why. Now, let me say this. Rationalizing denominators is important. It's important because if these are algebraic expressions with variables, you have to know that you can do this. Like, you know, if this was something like, I don't know, x over root x minus 1, and you wanted to rationalize this, right? Because maybe you needed to take the derivative and you didn't want to root down there or something, whatever. You need to know that you can multiply by root x minus 1 on top and bottom. So the actual skill is important. But when it comes to numbers, there's no need to turn this into this. The book will always do that, though. The answers, they'll always rationalize. But it's not necessary, is what I'm getting at. Okay? All right. Let's move on. You know, do you know that that's also why when you write natural log of x, that's why you don't write log base e of x? Because these are exactly the same thing, right? You have, when you talk about logs, logs can have any base, right? Any base, as long as this number down here is a positive number, right? And it's not 1, then you have logs. When the base of the log is e, you use that, and when the base of the log is 10, you use log x. And the reason why is because these are used so much that in mathematical papers back in the day when people were typing research papers and dissertations, and they would have this appear, this log would appear in their paper maybe 800 times. Typing it is a real pain in the ass when you subscript. If you've ever used a typewriter, which I'm sure you haven't, you type, you have to like stop, and even in a word processor, would you agree that even in a word processor, subscripting is not the easiest thing to do unless you know a shortcut key for it, right? So what we did is we said, look, this is used so much, let's just turn it into this, so that way if you're ever typing it or writing it or anything like that, you don't have to stop, you just keep going. That's it though, that's the reason why we do it. That's why these two logs look different than all the others. All right, history lesson's over. Get back to the fun stuff.
Why didn't they just make it easier to subscript? Or why do you think?
Oh, I don't know. Yeah. Not a lot of people subscript.
Is there a math history class, or do you just pick it up?
I think I've just picked it up. Yeah. But there are some classes, yes. I never took one, though. I had the option to take some elective courses, but I figured I could always figure out the history, you know. All right. How about a linear expression over a repeated irreducible quadratic? So what we just did was a linear over an irreducible quadratic, right? This one is a linear over a repeated irreducible quadratic. How do you mean split it up? Oh, you mean like do this over this, this over this? That would be reasonable. I think 1 over this we'd be in business. No, would we? Would 1 over this, would we be in business 1 over this? It's squared though. See, it's x squared plus 1 squared. That wouldn't, arctangent wouldn't work. And if I had just 1 over that, I couldn't let x squared plus 1 be u. Because du would be 2x, and I don't have 2x up here. What did we do in the previous one? We had linear over irreducible quadratic, right? What did we do there? I tried to make the top be the derivative of the quadratic part, right? Let's try that again. Let's try that again. What I really would like, yeah, you could expand this, then it would be a 4th degree polynomial, right? Okay. Let me just try this. I really wish